Welcome back to this course on blockchain and its applications. So, in the last class, we have seen the permissioned blockchain architecture and we have discussed briefly about how you can achieve consensus in the context of a permission blockchain network, and what we have seen that we can use this state machine replication concept from the classical distributed system architecture to implement consensus mechanism in the context of a closed blockchain network. So, in this context today we are going to look into the details of the state machine replications and how state machine replication can be used for distributed consensus and its connection with permission blockchain models. So, today we are primarily going to cover the state machine replication as a consensus technique, followed by the synchronous and the asynchronous consensus ideas in the presence of one particular type of failure which we call as the crash fault. So, these are the keyword. Today we are going to look into the crash fault tolerant system, and we are going to have a brief introduction about one of the consensus mechanism which is called Paxos. So, let us start with having a discussion about how state machine replications can be utilized as one of the consensus mechanisms. So, what we have seen in case of state machine replication, so it is something like that. The state machine architecture, it works in this way that every individual replicas that I have, they maintain a state machine, and I need to ensure that all the replicas are maintaining the same state of the system, right. And this particular idea is somehow close or somehow similar to our idea of consensus, where multiple participants need to agree on a common value, right. So, in case of state machine replications, the replica need to agree on a common state, and in case of my distributed consensus or kind of consensus in the permission blockchain, the participants who are there, they need to agree on a common value. Well, from this perspective, there is a natural reason to use such kind of state machine replication based consensus model over permission blockchain architecture, primarily because of these reasons. First, the network is closed, and when the network is closed, that means the participants or the nodes of the network, they know each other. Well, so when the participants or the node of the network knows each other, so you can do state machine replication among the nodes. Well, so what does it mean? That means that in case of a closed network, you can just think of every individual node as a replica, and when every individual node is considered as a replica, at that stage you can possibly think of that, well, there exists a state machine and this state machine gets replicated across all the replica, and if this replica agree to a common value of the state machine, that means or if this replicas agree to a common state of the state machine, that means the corresponding nodes, they agree to a common value in the context of blockchain consensus. So, with this particular idea, we can try to map the state machine replication problem as a problem for the distributed consensus on permission blockchain architecture. So, this is kind of one particular reason. The second reason is much more interesting. It says that, well, by applying such kind of message passing based architecture over state machine replication, we can avoid the overhead of mining. Well, so as we discussed earlier, that in case of permissionless blockchain or a open blockchain, the mining overhead is the significant overhead that we need to consider, and whenever we are avoiding such kind of mining stuff and we are just relying on message passing, we do not need to spend anything like the power, time, Bitcoin, whatever was there for different kind of mining algorithms that we have seen earlier, like proof of work, proof of burn, proof of elapsed time, proof of stake. So, everywhere you had certain things that you have to invest to show your membership, but here everyone is a member of the consensus group, and when everyone is a member of the consensus group, they can simply pass the messages among themselves to come to an agreement. Well, but as we have seen earlier that we still need consensus, because machines can be faulty, and when machines can be faulty, that means the corresponding nodes can behave maliciously. Well, the example that we have seen earlier, that if a particular machine is faulty, although after coming or after correctly executing the code on that state machine, everyone is likely to reach to a particular state, say state 2, one faulty replica may say that, hey, I have not reached to state 2, I have rather reached to state 3. Then you need to have certain kind of majority voting or such kind of architecture to reach to a consensus. So, that way we still need certain kind of consensus on the current state of the state machine that we can achieve by extending this particular idea. Now, with this objective, what we can do here is that we need a bit of redesign, well, on the basic consensus idea based on this simple message passing interface or the simple majority voting. Well, and what we will see later on that, well, crypto is the saver here. We can basically combine the classical distributed consensus algorithm with cryptographic technique to design consensus algorithms for the permission blockchain network. Well, so that is the advantage that we have. Indeed, the recent consensus algorithms that have been proposed in the context of classical distributed system, those consensus algorithms also talk about utilizing cryptographic technique to release some of the assumptions that they made earlier. Well, so we will gradually see that what type of assumptions are made by individuals and how we can actually release those assumptions by taking help of cryptographic techniques like digital signatures, cryptographic hash and so on. So, what we can do that we can utilize the classical distributed consensus algorithms like this Paxos, Raft, Byzantine agreement protocols. So, all these are different type of classical distributed consensus algorithms. We will see them in detail and we can consider those algorithms, and interestingly all these algorithms are based on state machine replication. Well, so they use this state machine replication idea that, well, I need to have certain kind of message passing interface to come to an agreement based on the majority voting, saying that, well, all the replicas are on the same state, well, same state of the state machine. So, from that perspective we will gradually try to design the consensus algorithms for the blockchain. Now, just to start with it, let us try to revisit those algorithms for the classical distributed system, and then we will see that how we can apply those consensus algorithms in the context of blockchain consensus. So, before going to these algorithms for blockchain consensus, let us try to revisit the different type of faults that can happen in a distributed system. Okay. So, earlier we had seen them briefly. Now, the consensus algorithms that we are going to design, this fault architecture has a significant impact on our algorithm that we will see. So, that is why we need to understand or we need to characterize the different kind of faults that can happen. So, the first type of fault that we are going to discuss about are this crash fault. So, the crash fault basically means that the node which are there, it stops operating. So, that may be due to a hardware fault or a software fault. Now, interestingly, as you remember that we have two different type of communication channel. One we call as the synchronous communication channel, and the second one we called as the asynchronous communication channel. Now, in case of synchronous communication channel, we have seen that I have a predefined time bound t, which is actually very small, and it is expected that all the messages will be received within this time bound t. But in case of asynchronous consensus, I do not have such kind of time bound. So, that way the messages can received out of order or the messages can get arbitrary delay. Well, So this kind of properties we have seen earlier that can happen for an asynchronous system. Now, whenever we are talking about this asynchronous system, we do not know whether the messages have been delayed or the node is not responding. Why that is so? Because see, I have one node which is supposed to send a message. Now, assume that this node has crashed. If this node has crashed, that means you will not receive any message out of this particular node. But if you are considering about asynchronous system, in an asynchronous system you also have an arbitrary message delay. That way, even if this node has sent a message, it might happen that the message have experienced arbitrary delay, and that way you are not receiving the message. So that way the other node who is possibly waiting for some message from this node, this particular node which is waiting for the message, it can get a signal only when it receives certain message. So if it does not receiving any message, so it cannot say whether it is a fault or whether it is certain kind of delay. Okay. So it is difficult to actually characterize that. So under certain kind of system, to reach into the consensus, we rely on majority voting. So later on we will see that what particular protocol we typically use for decide about such kind of majority voting. So basically what happens that to reach to a consensus, every node waits for the votes from different other nodes, and once you receive certain number of votes, then you can say that, well, we have reached to a consensus and this is the value corresponding to consensus. Okay. So, but remember one thing, that whenever we are talking about the crash fault, so in the context of crash fault, the only thing which can happen is that you are not receiving a message. So it will never happen that you are receiving a wrong message. Well, so if you are receiving a wrong message, that is a different kind of fault which we are going to discuss later on. That particular fault we call as the Byzantine fault, but here we are just talking about the crash fault. So in case of a crash fault, either you will receive the message or you will not receive the message. Okay. But not receiving the message does not mean that the node has crashed, because you are in an asynchronous system, and in an asynchronous system you can have arbitrary delay on the message. So that way it might also happen that, well, the node has actually sent the message, but it is in a very slow network, because of which possibly the message got lost, or possibly the message got significantly delayed, because of which you are not receiving the message. Well, similarly, once you have received the consensus, then you can propagate this consensus information in the network, and for propagating the consensus information in the network, you still have the same problem. That means you might happen, it might happen that you have certain nodes which are in the slow network, but what we believe that it is a kind of eventual consensus. So everyone will get the messages eventually. It might happen that there is a long delay before which you are getting this consensus information, but eventually every node will get that consensus information. So this is the kind of context of the crash fault. Now the second type of fault, as I was mentioning earlier, that in case of crash, we just assume that the messages will not be received. It is not like that you will receive a wrong message. If you receive a wrong message, that is this second type of fault which we call as the Byzantine fault. Now in case of Byzantine fault, what happens that the node starts misbehaving, either due to an attack or maybe due to certain kind of fault, and it starts sending wrong information. Well, or rather what we say that it send different information to different peers. Well, say for example, this is say a Byzantine faulty node. So what this Byzantine faulty node will do, say it has two different peers. So it will send different information to different peers. So it might say that, well, I have received a 0 to one of its peer, and to another of its peer it might say that, hey, I have received an 1. Well, so such kind of behavior we call it as the Byzantine behavior. So why we call it as a Byzantine behavior, that we will see later on. So there is an interesting story from where this name Byzantine came from, but basically Byzantine behavior means that the nodes are trying to behave maliciously. And such kind of malicious behavior can also come from a context of security attack. Now, typically handling these Byzantine faults are much more difficult compared to the crash fault, but these Byzantine faults are more suitable for blockchain, because in the context of blockchain we assume that we need consensus because there are nodes which may behave maliciously, there are nodes which might give false information. So, I need to find out whether that information is false or correct, because of which this notion of Byzantine fault is much more important in the context of blockchain. But remember that this Byzantine fault tolerant algorithm, they have their foundation on the crash fault tolerant algorithms. So, this Byzantine fault tolerant algorithm, which we call as the BFT consensus. So, this BFT consensus actually came from this crash fault tolerant algorithms or the CFT consensus. So, because of that reason, it is also important to first understand that how CFT consensus works, then from there we will go back to Byzantine fault tolerant consensus and we will see that how Byzantine fault tolerant consensus work. Well, so if I directly go or directly jump to discussing about that BFT consensus algorithm, it will be difficult for you to understand. So, that is why we will start with this crash fault tolerant algorithm and gradually we will move towards the Byzantine fault tolerant algorithms. So, let us first try to look into this crash fault in the presence of asynchronous consensus. Now, the moment we are talking about this asynchronous consensus, we need to keep in mind about this FLP impossibility, which says that, well, in a pure asynchronous channel, you cannot ensure safety and liveness together even with a single crash fault. Well, so again in today's lecture I am repeating the same story about the FLP consensus, but as I mentioned earlier that while you are designing this consensus algorithm for any network, reiterating this FLP impossibility is important, because you need to ensure that, well, you cannot satisfy all the criteria for consensus simultaneously, and when you cannot satisfy all the criteria for consensus simultaneously, you need to give priority to somewhere. Well, and typically what happens that these crash fault tolerant algorithms that we are going to talk about and some of the BFT consensus algorithms as well, they give priority to safety over liveness. Well, so the objective is that whenever I am reaching to the consensus, so at the consensus I will have the information which is safe. Well, so safe means it is at the same time what we have seen that it is the kind of final information. So, what we call as the consensus finality. So, in the context of proof of work blockchain, we have seen that it does not reach consensus finality. So, you cannot reach consensus finality there, but in the context of distributed classical distributed consensus algorithms like Paxos, PBFT, the type of algorithm that we are going to see here, we will see that the safety is more having more priority over liveness, and because safety is having more priority over liveness, that is the reason that this consensus mechanism they sometimes compromise with liveness. We will also see that how we are going to compromise with liveness, and we will see that how we can reach to the consensus eventually by considering the safety and liveness criteria together. Now, the consensus algorithms that we are going to discuss about, it is going to guarantee these following properties. So, this is the standard property for any kind of distributed consensus mechanism. First is validity. So, validity says that if all correct processes propose the same value V, then any correct processes decide V. Well, and remember that we are talking about CFT or crash fault tolerance. So, the crash fault tolerance says that, well, a correct process means the process is running, it has not been crashed. Now, if that is the case, that the process is running and it has not been crashed, that means if a correct process is proposing certain value V, then all other correct processes will decide on V. Well, because no one is going to say something wrongly, because then that is in the purview of the Byzantine consensus, not in the purview of the CFT consensus. The second requirement is the agreement. So, agreement basically says that no two correct process decide differently. So, every correct process will decide on the same value, and the third one is called as the termination. So, the termination says that every correct process eventually decides. Well, so that means every correct process will eventually reach to the consensus. Now, if I just try to map this requirement with my standard requirement of consensus, what we will see that, well, this validity requirement, it is unlikely to happen in proof of work. Well, so earlier we have seen this proof of work consensus mechanism. So, validity is unlikely to happen because by virtue of that consensus mechanism of proof of work, it might happen that different miners propose different blocks. So, when different miners are proposing different blocks, then I have different blocks which are floating in the network, and as a consequently we need to ensure that I would select one of those different blocks which are there. The second requirement is the agreement, which is similar to the safety property, that no two correct process decide differently, but in the context of proof of work we have seen that might happen, that it might happen that two different nodes in the proof of work network, they decide two different blocks. So, although both of the blocks are correct, but structure wise they are different blocks. So, safety is not guaranteed or the agreement is not guaranteed there. What is guaranteed there or what is given more priority in the context of proof of work is the termination, which is similar to the liveness property. So, it says that every correct process they will eventually decide one of the block. Okay. So that way these are the kind of properties which are there in the classical distributed consensus algorithms, and they are reference in the context of the proof of work mining. Now, let us try to see that what happens when we talk about the consensus in case of a distributed environment. So, we are going to talk about the CFT consensus or the crash fault tolerant consensus. So, there are primarily two broad algorithms on crash fault tolerant consensus. One is called Paxos. Paxos is the kind of most fundamental CFT consensus algorithm. It was proposed by Leslie Lamport. It is the fundamental consensus algorithm as I mentioned earlier. Systems like DynamoDB, they basically use this Paxos to reach into consensus. There is other consensus CFT consensus algorithms like Raft. Raft is much simpler than Paxos. Raft is used in blockchain in one context. So, whenever we are talking about or whenever we are going to discuss about Hyperledger Fabric, we will see that for Fabric transaction ordering it uses Raft. Well, so the Fabric transaction ordering, if you assume that there are no Byzantine node in your system or there are no malicious node in the system, rather you are going to do the transactions ordering among a set of non-Byzantine node or non-malicious node, but it might happen that certain node might get crashed. So, in that context you can use this Raft consensus to reach to a consensus on that transaction ordering. So, we will see later on in Hyperledger Fabric that it uses Raft for transaction ordering. So, now we are going to look into how Paxos works, because as I mentioned that Paxos is the kind of most fundamental consensus algorithm, and if you can learn Paxos, if you can understand how Paxos works, it will be very easy for you to learn about the other consensus mechanism. So, that is why we will give or we will focus for giving more time on discussing about Paxos. Now, before going to Paxos, let us try to look into that how consensus works in the context of a synchronous system. Now, in a synchronous system, just think of an scenario that you and 4 of your friends, like 5 of you, after this lecture you want to go to somewhere. Well, you want to say assume that it is an evening, 5 of your friends, you collectively make certain planning and you want to go to somewhere and you do not have any leader among yourself. So, you will collectively decide that where to go. Now, if you are in a synchronous system, what might happen that just one of your friend might say that let us go for a dinner, and we are in a synchronous system. Well, so, whenever we are in a synchronous system, that means the moment I say that let us go for a dinner, within some predefined time threshold, or rather in real time, everyone will be able to receive this message if that person is awake. Well, so what say happens, say your friends who are currently awake, they are being able to pick up the telephone call and they agree to this message. Well, and one of your friends, say this black friend here, that person went for a sleep and that person do not receive the message. Well, so this person I can just assume like a kind of crash faulty node where some kind of crash fault has happened. So, the friends agree together that we can go for a dinner. So, here if you just think about the majority voting, so the majority agreed for a dinner, so you have a perfect consensus. Well, although one of your friend was sleeping. Now, if you just think about an asynchronous system, well, so in asynchronous system, what I say that the messages might get delayed. Well, now when messages might get delayed, what might happen, that one of your friend is waiting for your message and that person is not been able to get the message. Say for example, you have sent an SMS and that SMS got delayed, well, and that person is not receiving the SMS. So what might happen, that well, you might have proposed for a dinner. Now one of your friend has received that message, the friend sends another message saying that hey, I am in, then a second person it says that hey, I am okay, and in between this fellow who is far apart, maybe that fellow is in a slow network and have not received the message that have been sent by others. So that fellow have not received that message for dinner, and that fellow thinks of that, well, let me propose something myself. Well, and that fellow make a proposal that can we go for a movie, well, something a different proposal. Now it may happen that, well, this choice of movie that all of you found it preferable. So what might happen, that this particular friend it says that, well, I would prefer movie, it agrees to movie. Then another of your friends says that, well, movie is a better idea, and during that time there is a crash happens, that one of your friend, after that friend said agreed to that dinner, the friend thought of that, well, we are going for a dinner at 9 p.m. So I have some 3-4 hours in hand, so let me go for a sleep, and at 9 a.m. and 9 p.m. I will wake up, make a call to others and find out that what is the place where they are going, and I will join them. So that friend has thought of like this and just went for a sleep. So that friend has not received these new messages, like that new proposal that someone has said to go for a movie, but by that time that others have found out that, well, movie might be a better idea compared to a dinner. So they agreed on movie. Well, so here what we see that, well, majority of them have agreed on movie. Now when majority of them have agreed on movie, so you have a consensus on a movie. Now you decided together that, well, the plan is to go for a movie. Now this friend who went to sleep, he or she wakes up at say 8:45, makes a phone call and say that, hey, are we going for a dinner, right? Because that friend has not received that updated messages, because he or she went for the sleep. So that is equivalent to the crash fault which we are talking about in the context of the system. So that friend has not received the message, but here you have already received in a consensus. So what you can do, that you can just inform that consensus information to your friend, saying that no, we have decided for a movie and we have not received any reply from you, so we thought of that you also agree. Well, so with that friend, well, that is the kind of consensus, majority have already agreed on going for a movie. So that person has no other option to go for a movie if they have to obey this majority consensus things. So that way what we can see that, well, we can still reach to a consensus in an asynchronous system, but in an asynchronous system, to guarantee that majority of the people actually replies back, what I can do, I need to ensure that no more than 2 people are sleeping at a time. Well, so you have 5 of your friends, if 3 of them are sleeping, then you cannot reach to a consensus, because you will not get the voting from the majority. Well, so that way once you are getting 3 votes, you can see, you can know that, well, we had 5 in our group, so I have received 3 votes. So, that is the kind of majority, so we can go with that. So, this is the kind of idea of the crash fault tolerant consensus in an asynchronous system, and we are going to design a protocol for supporting CFT consensus in an asynchronous system. So, this asynchronous CFT, what it says that if there are F faulty nodes, then we need at least 2 F plus 1 nodes to reach consensus. So, why that is so? So, that is possibly clear to you from that example, that out of the 5 nodes you can have at most 2 node as faulty, that means 2 of your friend can go for a sleep. Now, in this context we are going to discuss about Paxos. So, this Paxos is a family of distributed algorithms to reach consensus in an asynchronous CFT. So, remember that Paxos is not a single algorithm, it is a family of algorithm, it is a set of algorithms. So, we are just going to look into the vanilla Paxos, the basic version of the Paxos. So, this Paxos algorithm, it was proposed by Leslie Lamport in 1989. It received a lot of criticism about its proof of correctness, and finally, it got accepted in ACM Transactions and Computer Systems in 1998, and the title of the paper is The Part-Time Parliament. Okay. So, I would suggest all of you to look into this paper. This is a very fundamental paper about distributed consensus, the Part-Time Parliament paper. And what you can see that when the algorithm got initially proposed in 1989, after that it took around 9 years to get that algorithm accepted and get people convinced that this algorithm actually works well. And finally, Lamport received this Turing Award in 2013 for his contribution in this distributed consensus and in general in the design of distributed systems. So, in conclusion, what we have seen that consensus is harder on asynchronous environment. We always have a trade off between safety and liveness, and for an asynchronous CFT we need 2 F plus 1 node with F number of crash fault tolerant node, and we have just touched Paxos, which is a kind of very fundamental crash fault tolerant algorithm, and in the next class we are going to explore Paxos in details. So, thank you all for attending this lecture. So, we are going to meet in the next lecture with the details about Paxos.